to week 11 of advanced algorithms. This week, we are going to be introducing yet another framework for thinking about algorithms beyond the worst case. And this is called parameterized algorithms, although sometimes the phrase multivariate analysis is also used to refer to the same kind of set of ideas. And this is a paradigm that gained traction in the 90s, and it's only grown in popularity since, and is currently a very active area of research. And it ties in very nicely with some of the other paradigms that we have seen. So there's a lot of opportunity to combine ideas from what we are going to see now with things that you've seen already in terms of randomization and approximation and so on. And we might even see a few examples of that happening as we go along. So this week we are going to talk about parameterized algorithms, and next week we are going to talk about kernelization. That's where we wrap things up. And kernelization turns out to be sort of a formal framework for reasoning about heuristic algorithms, and that's very exciting, and it kind of builds on the foundation that we are going to establish this week. So let's just get started with this. I should say that I'm going to be borrowing mostly from this lovely book called Parameterized Algorithms, and it's written by a group of authors whose names you can see on the screen. They have contributed to a lot of contemporary research in the field, and this book was definitely a reflection of the state of the art when it released a few years ago. And while on some specific problems, developments have happened since, so the book may not reflect the latest and the greatest for a given problem, it's still very much relevant in terms of communicating a lot of modern ideas in the field. The field has been lucky to have had a lot of great exposition around the main ideas in it. So there are a few other books as well, and you can find links to them in the course resources. So I hope that if the trailer that you see with the with whatever we see this week is exciting enough, you have a chance to go and check some of these books out, which go into these things at much greater level of detail, of course, and cover much more as well. So there's only so much that we can do in a week, but I'll try to pull out a few of the highlights, which really are a bunch of charming examples of how this way of thinking about problems can really open up a whole new set of ideas. So what's the basic premise? Well, whenever we are thinking about how we report the performance of an algorithm, not only are we often thinking about worst case, just so that, that's the pessimistic approach where we just want to be covered for all possible scenarios. But not only do we talk about worst case, but we also describe the performance of an algorithm typically in terms of one or two parameters. So usually we report the performance in terms of the running time, and the running time of an algorithm is usually described as some function of the input size. And so you can think of this as sort of a univariate approach to things. This is a function of a single variable, which tries to encompass information about how the algorithm does in the worst case. And of course, some people might also concern themselves with the space complexity. So maybe there will again be some function that tells you how much space the algorithm is going to consume, again in the worst case usually as again a function of n, which is again the size of the input. And the point here is that sometimes just thinking solely in terms of the size of the input can be a slightly limiting perspective, because there's only so much you can do with it. Just to give you maybe an example that's familiar from undergraduate algorithms, think about how you report the running time of breadth first search. So we know that breadth first search has a worst case n plus m complexity, which sometimes gets reported also as order n squared. And thinking of it in terms of order n squared is not wrong. It's certainly a valid upper bound for the running time of BFS. In fact, that's true, irrespective of what data structure you use to implement your graph. But there is more nuance to this, and with the right implementation, we do know that the worst case running time is in fact n plus m, and we often think of this as a linear algorithm. And the reason for that is, of course, that n plus m is a true reflection of the size of the input, and the running time is linear in that, as opposed to being quadratic in the number of vertices, which, like I said, is a valid upper bound. But let's just think about why this style of talking about the running time actually conveys more. It conveys more because it tells you that if, for instance, your graph is sparse, let's say your input is a tree or something, and then you know that m is n minus 1, or let's say generally have a sparse graph where m is order n, which is to say that the number of edges is linear in the number of vertices. In all of these circumstances, this running time here actually tells you that your entire algorithm is going to be linear in the number of vertices. You know this because you can look at the running time and you can say that, okay, that's linear in n and m, but for me, m is already linear in n, so I know that I have an algorithm which is basically order n. Whereas if you have a dense graph, where let's say, for example, you have a complete graph or something like that, the other end of the spectrum, then you know to anticipate that, well, now the algorithm is likely going to be slower on these kinds of inputs. So you get to see a spectrum already based on how many edges the graph has. So the algorithm is faster for sparse graphs and is slower on dense graphs, which is the sort of information that you're not going to get if you simply report the running time as order n squared, which, like I said, is not technically wrong, but it just communicates less information. But now imagine that you think of your running time in terms of other aspects of the input. So here we are looking at the number of vertices, the number of edges, but maybe you could also think in terms of the maximum degree of the graph, or the diameter of the graph, or some other aspect of the graph, which maybe you can actually, now that you're thinking about, well, is my algorithm faster in terms of some of these things, then you can also now go back to the drawing board and try to design algorithms keeping in mind that we want it to be faster along these axes. And why would you want to do that? So maybe you're in a situation where you know that your inputs, let's say, typically have low degree, for instance. So then maybe if you can design an algorithm whose running time is, let's say, n times d, where d is the max degree of the graph. Again, this sort of thing tells you quite a bit about the behavior of the algorithm. You know that if the maximum degree of your graph is some constant, let's say you're looking at subcubic graphs, which would mean that every vertex has degree 3 or less. In that case, this is effectively a linear time algorithm, right? Of course, we know that in the worst case, the degree of a graph can be as large as n minus 1. So in the worst case, we know that this is a quadratic algorithm. But in the best case, it could be as nice as being linear. And you know that those best cases manifest when the degrees are constant, or when the degrees are really small. Now, turning the tables around, if you are in a situation where you know that your input happens to have this nice structure, it could be that it has low degree, it could be something else, then you could ask yourself, well, can I design an algorithm whose running time is such that by design you exploit this structure and you get faster running times on your particular slice of the input. So here you're really trying to take advantage of additional information that you might have about your situation, and then you go back and think about, well, can we leverage this? So far the examples that we have talked about involve graphs, but this general idea really applies to several settings. For example, you could think about scenarios where your input is not a graph but something else, say a program, for instance. So compilers work with programs as input all the time. And when you're dealing with programs, well, the typical single parameter setting, you're probably thinking about the length of the program or the number of lines of code in the program. But what else can you analyze a program in terms of? Well, for example, think about the maximum nesting depth that you're likely to encounter in a program. That's probably typically a small constant, right? You don't usually nest too deep, at least not in human generated code. And therefore, if you had an algorithm whose running time was of the form, let's say it's exponential in the nesting depth of the program, the maximum nesting depth, but it's polynomial in terms of the lines of code, then this is probably going to turn out to be effectively a polynomial time algorithm in practice, even though in the worst case, the nesting depth could be linear in the length of the program, but that's a situation that you're very, very unlikely to encounter. And in fact, in Spirit, there are algorithms of this form that compilers use all the time. So in fact, one of the interesting things about the parameterized framework is that it can also be used to retrospectively explain why some algorithms that have been around for the longest time actually work. You take a closer look at what's going on, and it turns out that if you think of the running time in terms of just chunking it up into these components, then that might explain things quite a bit. So that's an interesting aspect of the multivariate approach to reporting performance. Now, maybe let's just look at a concrete example of an algorithm for a familiar problem. So we've talked about vertex cover several times, and let's just recall that in this problem we have a graph as an input, and let's look at the decision version of the question. So we also have a number k, and the question that we're interested in is, does G have a vertex cover of size at most k? And recall that a vertex cover is simply a subset of the vertex set, such that if you were to remove these vertices, then you're left with an empty graph. So there are no edges that remain. So every edge has at least one of its endpoints in the set S. So we have looked at vertex cover before in the context of finding approximate solutions, but now let's think about designing an exact algorithm, which would mean that we do want to be accurate in our outputs. So we want to either determine that G has some vertex cover of size at most k, and if this is the case, ideally we want to also output this vertex cover, although we could for now simply focus on being able to say yes if there is a vertex cover of size at most k and no otherwise. And this time we want to be completely confident in our answers, so we don't want to report this correctly with high probability or anything like that. We want to be sure about getting this right. And one brute force approach to this would be to just try all possible subsets. So you could do that. And of course, you might realize that you don't need to try all of them. You only need to try the ones that have at most k vertices, right? So try all possible subsets of size at most k. And for each of these subsets, test if it's a vertex cover or not, right? So in fact, if you don't care about optimizing for size, you could just look for sets that have size exactly k And if any one of them turns out to be a vertex cover, we can say yes, and otherwise we can say no. So we would be going over n choose k subsets in this process, right? The if we didn't restrict ourselves on the size, if we didn't do that, then trying all possible subsets would have taken us time proportional to 2 to the n. So already we have, in some sense, an improvement, which is nice, but it turns out that even an n choose k running time can be quite infeasible even for seemingly small instances. So, for example, if n was 1000 and k was just 10, then 1000 choose 10 is already more than 10 raised to 23 times 2 or something like this. So you can appreciate that even for instances that look like not gigantic, we are already stuck with a pretty prohibitive running time. So the question we ask ourselves here is if we can do better. Of course, that's our favorite question to ask, and it's something you ask all the time. But in this case, it turns out that happily the answer is yes. We can, in fact, do significantly better in this example. So let's try and develop a branching algorithm for vertex cover. The ideas would be similar to what we did when we were talking about branching, in the context of exact exponential algorithms. But this time, hopefully, we will be able to knock out the recursion tree earlier than what we are used to from before. And this is because intuitively we have a limited budget that we're working with. So we're working with a concrete task of coming up with a vertex cover of size at most k. So maybe let's just go ahead and talk about the branching algorithm and see where it takes us. So our basic unit here is going to be a single edge. So pick your favorite edge in the graph. Let's say it's UV. And what we know about any vertex cover, either the one that we are after, which is one of size at most k, or really just any vertex cover in this graph, including the small ones, would have to cover this edge, right? So let's say, for the sake of analysis, let's say that we are hypothetically dealing with a yes instance, which means that there is a vertex cover. So there is a subset of vertices of size at most k such that for every edge UV, S picks up at least one of the endpoints. So it may pick up both, but it certainly picks up at least one. This we know for sure. So when I pick an edge in the graph, although I don't know anything about what S looks like, I do know that it has at least one of these two vertices. So that gives me a branching strategy. So on the one hand, I'm going to commit to picking U in the vertex cover, and on the other hand, I'm going to commit to picking V. Notice that these are not mutually exclusive choices. When I'm picking U, I'm not saying that I will not pick V in my vertex cover. As you will see, V is going to very much be around in the instance that we generate in this part of the branching, and will remain available to be chosen by the vertex cover later if that's what turns out to be what needs to be done. Okay. So in this branch, we are going to make a record of our commitment by saying that, well, first of all, we've decided to choose U. So we are going to move to the graph G minus U because the vertex U has now done its job. And the fact that it's chosen in the vertex cover means that our budget for the vertex cover goes down by 1 because now we have decided to incorporate U in our solution. So we start off with the instance G comma K, and in one branch we look at the modified graph which is G with the vertex U missing, and the budget adjusted by 1. And you can probably guess that in the other parallel universe that we go into, we are looking at the graph G minus V with again a reduced budget of K minus 1, because in this case we are incorporating V in the vertex cover. And like I said, it's a common point of concern for some of us when we see this algorithm for the first time, where we think, well, shouldn't we have an additional branch which accounts for the possibility that U and V are both in the vertex cover and the budget reduces by 2? It seems like this should be the natural thing to do, so that we are comprehensive and we have explored all possible ways in which this can happen. But if you think about it, you'll realize that, well, you could, of course, implement a branching algorithm that looks like this, but it turns out that it'll be redundant, because whatever happens in this branch here will, in fact, be captured in one of the first 2 branches. So if the vertex cover that we are after, let's say that there is a unique vertex cover of size at most k, and that happens to choose both U and V, well, it will be the case that such a vertex cover will get caught out in one of the branches that come up in the future, because presumably after you have picked U, the reason our vertex cover also needed to pick V is because V is incident to some edges which need to be covered, and those edges are going to very much be around in the graph G minus U. And when you choose to branch on one of those edges, then what's going to happen is that in one of those branches, V will get chosen as well. Or on the other hand, it could be that you choose to pick V first, and then there are edges that are still incident on U. And indeed, if there is an optimal vertex cover that picks both U and V, when you branched on these edges that still remain on U, on one of those sides, you would have chosen to pick U. So this UV scenario will basically manifest somewhere down here in one of these branches. So that's something that we don't need to do explicitly, and that saves us some time in the analysis. Okay, so now let's talk about when does this algorithm terminate? What's the terminating condition? Because we've just described the recursion, and we need to talk about the base cases. Well, there are 2 natural places where we get stuck. One is if we don't have any budget left. So when we run out of budget, that's one natural place to stop. So if at some point k becomes 0, then we look at the graph and we ask if the graph still has edges left. So if we have a non-empty graph and the budget is 0, then at that point we can say no. So that would be one of our base cases. But the other thing that can happen is that you run out of edges to branch on before you run out of budget. So in that case, you have nothing left to do. This essential step of picking an edge to branch on is no longer available if you've exhausted all the edges. But this is good news, because that means that you've actually found a vertex cover before running out of budget. So if it turns out that you have no edges left, so that is the E of G is the empty set, and implicitly we know that k is non-negative, then we can report yes, and those basically seal the algorithm, right? So as long as you have budget and you have an edge, then you have at least one edge, then pick an arbitrary edge to branch on, and the budget reduces in both of your branches when this happens. At some point, you will either run out of edges to branch on, or you will run out of budget. At that point, you stop, and you know what to say. So that's essentially the entire algorithm. And if you think about what the recursion tree looks like, well, we're doing a 2-way branch at every step, and the number of steps that we have to recurse is bounded by at most k, because every step in this recursion reduces the budget by 1. So the depth of this branching tree is at most k. So using techniques that we know that we're looking at a running time that's 2 to the k, and that's the number of leaves in this branching tree is 2 to the k. So um, asymptotically, the overall running time is bounded by the total number of nodes in this branching tree and multiplied by the amount of work that is being done at each node. So the overhead here is basically polynomial. This is because all that we have to do at every node is find an edge to branch on, check if our budget is non-negative. We want to check if we have at least one edge to branch on, and then once we have decided on what edge we're going to carry out the branching on, all we have to do is a g minus u and an updating of the budget. So removing a vertex from the graph, all of that is basically polynomial time. You can come up with slightly tighter bounds perhaps, but we are going to basically say that we have a poly overhead on top of the size of the recursion tree, which in this case is bounded by 2 to the k. So that's essentially our first bounded search tree approach in the context of parameterized algorithms. So what's the parameterized aspect here? Well, notice that we went from what we had earlier, which was something like n to the k, to 2 to the k poly n. And the main improvement here is that we have managed a separation of the n versus the k. So you might have guessed already that in this case, we're thinking of k as the additional parameter by which we are measuring our running time. So k happens to be, in this case, the budget. So as opposed to being a structural aspect of the graph, like we said earlier, you could be thinking about maximum degree, or you could be thinking about diameter. That's not the parameter in question here. The parameter is the number of vertices that we allow to pick in our solution. In general, you can choose to describe the running time of your algorithm as a function of whatever parameters are relevant to you. For optimization problems, especially ones that are minimization problems, you would probably expect the budget or the size of the solution that you're looking for to typically be small. So it's a very natural choice of parameter. And even for maximization problems, sometimes it's just a natural place to start. And that's why the budget associated with an optimization problem is often called the so-called standard parameter, because it's the default thing that comes to mind on top of the input size. So in this case, we would say that the vertex cover problem is fixed parameter tractable with respect to the standard parameter or with respect to the solution size. And what that means is the following. It means that we have achieved a running time which looks like this. It's some function of k, where k is the parameter in question, and the rest of the running time is a polynomial in n. What this means is that we have somehow managed to confine the exponential part of the running time, the expensive part of the running time, if you like, to being a pure function of the parameter alone, right? And the input size, which is potentially the thing that is large, right? That has the running time associated with that is only polynomial, which is our traditional concept of efficient, right? So this separation, whenever we are able to achieve it, we say that the problem with respect to whatever this parameter is fixed parameter tractable. Let me write this down. And this is sort of a fundamental concept in the context of parameterized algorithms. We're always trying to design fixed parameter tractable algorithms because in general, that's a really nice situation to be in. And of course, once you have some fixed parameter tractable algorithm, you want to know if you can do better even in this context. So for instance, what we have for vertex cover is 2 to the k poly n. And that's asymptotically the case. And now you could ask yourself, can we improve this to say, for instance, 1.5 to the k poly n? That would be faster. And some people also like to look at trade-offs between the f of k versus the poly n. So there is, for example, a lot of work that's been done around linear time FPT algorithms. So by the way, I will often use FPT to refer to fixed parameter tractable. That's a pretty standard shorthand. So that's that's one of the most foundational notions that we have here. So fixed parameter tractability is often what we are after. And notice that what the name already implies is that the problem is tractable, meaning you can solve it in a reasonable amount of time for fixed values of the parameter. Compare this with the kinds of running times that we saw before. So we have seen pure exponential running times where there are no parameters in the picture at all. And these are typically functions just of n. And that was our first algorithm for Vertex cover. We said you could just brute force through all your subsets, and that would be 2 to the n with some poly overhead, presumably. And our first improvement was to this n choose k poly n. And here the general form of this running time looks like basically n to the some function of k poly n. So these running times are basically what are called slice-wise polynomial running times, and that's abbreviated as XP. And what that means is that, well, if you again fix a value of the parameter to being a constant, right? So let's say k equals 3 or k equals 5 or k equals 126, whatever it is. When you substitute in a specific value of k, you do end up with a polynomial running time overall, because n to the some function of a constant is still n to a constant. But notice that the polynomial itself changes as you change the value of k. Whereas here, this polynomial here, the polynomial overhead is fixed and it's not affected by changing values of k. So FPT is it's a more tractability concept, and the XP running times are nice, and a lot of problems have them. And in fact, there are problems for which we don't expect to see FPT algorithms, but they do have XP algorithms. And there are also problems for which we don't even expect to see XP algorithms. So that there is a hardness framework that allows you to reason about the absence of or the unlikelihood of the existence of certain algorithms for certain problems. In fact, we can already reason about the unlikelihood of certain XP algorithms based on what we already know about NP hardness. So for instance, recall that the 3 coloring problem, which asks if you can partition a graph into 3 independent sets. So basically we want all these edges to go across. We know that this is a hard problem, right? This is NP complete. And therefore, if you spend a moment thinking about what can we say about k coloring parameterized by k, the number of colors, you realize that even an XP algorithm is something that we don't expect for this problem, because even when k is fixed to be a constant, and indeed even when that constant is just 3, we already know that k coloring is NP hard, right? So that already rules out the possibility of XP algorithm for k coloring parameterized by k. Of course, you could think about, in this case it would make sense to think about other choices of parameter for the coloring problem, right? So you could think about, for instance, 3 coloring on graphs that have small maximum degree, for example. Or given that we know that many problems are easy on trees, can we think about graphs that are tree-like in some sense? And would that be a useful parameter. If we could measure closeness to a tree, then could we use that to parameterize these kinds of problems. So these, in contrast to the standard parameter, these are called, generally speaking, structural parameters, because we are trying to peek into the structure of the instances and say that, well, if you have some structure that can be quantified in some appropriate fashion, then can we parameterize the problem from that perspective. So let's talk about one concrete algorithm in the context of a structural parameter. So let's think about the problem of finding a largest clique. So let me just recollect this problem. So the input is again a graph G and a number, which again we would normally think of this number as being the standard parameter. So this is K, and the question is, does G have a clique of size at least K? So that would be a subset of vertices where all the vertices are pairwise connected. So for all U, V, and S, we have that U, V is an edge. That's what we're looking for. And of course, as we said earlier, we do want the size of this set to be at least K. So that's the problem of finding a largest clique. And it turns out that this problem is, as far as we believe, this problem is not fixed parameter tractable. So just like we've said that there are problems that we don't expect to have polynomial time algorithms for because of the framework of NP completeness, there's an analogous framework in the parameterized world which informs us about certain problems being unlikely to be FPT parameterized by certain parameters. So for now, let's just take it as a given that under some appropriate complexity theoretic hypothesis, we cannot come up with an FPT algorithm for the problem of finding a clique of size at least K parameterized by K. So let's switch gears a little bit and consider instead one of the structural parameters that we've been talking about. So in particular, let's see if we can parameterize this by the maximum degree of the graph G. So in other words, we are asking ourselves, does the problem become easier on graphs where the maximum degree is bounded? And indeed, we do have this intuition for a clique that the size of a largest clique cannot exceed the maximum degree. So for example, if you have a graph G where the maximum degree is, let's say, 20, then you know that the size of a maximum clique cannot exceed 20. And the reason for that is if you look at a set of vertices which is larger than, let's say you have, well, maybe I should have said that the size of the largest clique is bounded by 21, because suppose you have a collection of 22 vertices or more, then pick any vertex in that collection. It can only be neighbors with at most 20 other people, because that's the maximum degree. We know that that's bounded by 20. So any vertex in this group can only see 20 other vertices in the group, maximum. So there will be, if there are 22 vertices or more, then there will be at least one vertex that you're not neighbors with, right? That this chosen vertex is not a neighbor with. Therefore, this fails to be a clique. So basically, the size of a largest clique is bounded by the maximum degree, or the maximum degree plus 1. Yeah. So one thing that might immediately come to mind is, well, then we can just try all possible delta plus 1 sized subsets of the graph, because we know that that's the best we can hope for. And in particular, well, we may not be lucky in finding a delta plus 1 sized clique, so we'll probably have to try all possible L-sized subsets, L ranging from say 2 to delta plus 1. And you could make this a little bit more sophisticated by saying that you'll do a binary search on guessing the size of a largest clique. The range for that search is going to be between 1 and delta plus 1. And once you have a guess, you say that, well, I believe that the size of the largest clique is going to be L. Let's try to validate this. Then you'll try and go over all the n choose L sized subsets. If one of them happens to be a clique, then fantastic. You know that the size of the max clique is at least L. So you move on to the next largest value of L. The next larger value of L in your search. And if you fail, then you know that the size of the max clique is less than L, so you move on to the next smaller value in your search. So you could do all of that. But still, your running time has this XP-ish flavor because we're looking at n choose L right now. And the question is, can we improve this to something that is FPT in delta? Is that possible? And it turns out that the answer to that is also yes, because what you can do is, instead of trying all possible subsets, you can guess a vertex that belongs to the clique. And this is the key idea here. So let me write this down. And just to be clear in terms of what I mean by this is really just a for loop that goes over all the vertices. What we are trying to say here is, well, there is a max clique. It contains a bunch of vertices. We have no idea what it looks like. So let's pretend that my favorite vertex V is in the max clique. And once we commit to this pretense, we are going to say, well, what does the rest of the max clique look like? Well, I know that if V has to be in my max clique, the rest of the max clique can only be a subset of the neighborhood of V, because everybody that's not neighbors with V is immediately disqualified from belonging to this hypothetical max clique, right? So we rule out a whole bunch of vertices once we commit to the idea that V belongs to my solution. But notice that V has only 20 neighbors, so we just have to try all possible subsets of this 20-sized neighborhood. And maybe our presumption that V belongs to a max clique is wrong, so we have to try this for all vertices, and we know that there must be some vertex that does belong to the max clique. So one of those guesses is actually going to be the correct one. And in fact, there will be multiple guesses that are correct, because if the max clique has, say, 12 vertices, then there'll be 12 guesses that are accurate. So that's fine. The point is that there's at least one that works. So the running time of this algorithm is indeed going to be something like 2 to the delta of G. And of course, there's going to be a poly overhead. And I may not always write it, but all my running times are in asymptotical terms. So you might have constant overheads, or yeah. So that's just me being lazy about not always writing this in order notation, but that's implicit. But this is our second FPT algorithm, and this time we have one that's with a structural parameter. The first one that we saw with the branching was with a standard parameter. And the last thing that I want to say is that it might occur to you that we can transform problems just like we did when we were talking about max flow, for instance. So one question that might occur to you is the following. So we know that independent set, we want to know if there is a subset of vertices of size at least k, where every pair of vertices are mutually non-adjacent. That's the independent set problem. And we know that independent set reduces to vertex cover. And that's simply because, well, if a graph has an independent set of size at least k, that's if and only if the same graph has a vertex cover of size at most n minus k. And we've just seen that vertex cover is FPT. We have a 2 to the k poly-n algorithm that we just designed. And you could ask yourself, well, does this mean that I can use this reduction to argue that independent set is FPT as well, because we've had this philosophy with reductions where we've said that if you reduce to a problem that you know how to solve, then you've solved your problem as well. But in the context of parameterized algorithms, well, we do have to be a little bit careful, because if you really unravel the mechanics of what's going on here, what's the plan? How will we use the FPT algorithm for vertex cover to come up with a FPT algorithm for independent set? Well, one way to do it would be, well, or the traditional way to do it based on the reduction would be to say, well, my algorithm receives an instance of independent set as input. It's going to transform it to the vertex cover instance and then run the algorithm that we already have for vertex cover. But the issue here is that, well, you have this instance of independent set and you have this transformed instance of vertex cover, which is Gn minus k. And you could run the vertex cover branching algorithm on this transformed instance. There's no problem. But the point is that when it runs, it's going to take time 2 to the whatever the size of the vertex cover is that you're looking for with a polynomial overhead. But the problem now is that the size of the vertex cover that you're looking for is n minus k. So this running time is no longer FPT in the original parameter k. So while this is a valid reduction in terms of preserving equivalence, so if whatever your algorithm reports, it's going to be the right answer, but it's not a FPT algorithm because the reduction does not preserve the parameters. So when you're doing reductions in the FPT world to leverage algorithms that you already know, it's a great idea and it often works. But the point that I want to emphasize here is that you do have to be careful about the details of your reduction. You have to make sure that the parameter is transformed in a way that keeps the FPT-ness of the whole procedure intact. So in this case, the parameter has blown up beyond control. It's gone from k to n minus k. And when n starts getting involved, things get corrupted. If you could have come up with a transformation which preserves the parameter, meaning that it goes from k to say k squared or even 2 to the k, you would still be in business. It would still be a valid FPT reduction. But as it stands right now, independent set does not reduce to vertex cover. And just as a piece of trivia, I should say that independent set is again one of those problems that's unlikely to be an FPT. And if you want to think about why, if you believe that clique is unlikely to be an FPT with the standard parameter, because we just mentioned that as another piece of trivia, if you want to believe only one piece of trivia and derive the other one, you can think about applying a reduction from clique to independent set that's parameter preserving and derive that independent set is at least as hard as clique in the parameterized world. Okay, so that's something that I'll leave to you as food for thought. And the other thing that I would like you to think about, just for fun, is to see if you can improve our branching algorithm for vertex cover. So we had something that looked like 2 to the k, and we asked ourselves, can we do better? Can we push this to, I said 1.5 to the k, which is really a totally arbitrary suggestion. It turns out that you can improve the algorithm, and in the literature it's been improved quite a bit. But if you think about it a little bit and try to either do something different, like maybe branch on vertices instead of edges, and see if you can tighten up the base cases a little bit and try to come up with earlier stopping conditions. Think about graphs on which vertex cover is actually easy to solve, can be solved in polynomial time. Can you exploit that? See if you can piece some of these hints together to think about an improved branching algorithm for vertex cover. So I think that's the other thing that I will leave in as something to think about. And if you do decide to take this up, we will have guided practice assignments that explore this question, and you can also find more information in the book that we cited in the beginning. So have fun exploring, and in the next videos we will be looking at more techniques for coming up with FPT algorithms for various problems. So see you next time. Thank you.